The title of this evening's talk is Distances and Distance Scales, and what I'm going to do is take you through how we measure distance in astronomy at various scales. And I'm kind of going to do this from a historical perspective, so I'm going to introduce you to some various historical figures through the ages who have developed these different distance measurements. But before I get into the talk proper, for the benefit of people who are watching this after the event on our YouTube channel, I just wanted to say a little bit about Mansfield and Sutton Astronomical Society and what our plans are. So this is where we're based, at Sherwood Observatory, and that's the white building there, of course. But I just wanted to draw your attention to the area that's surrounded in red there, and in particular that sort of circular area that derelict building centred on. If you go down through the roof of that building and through the floor, you end up here, which is an abandoned Victorian reservoir. And what our plans are to turn that into a science discovery centre and planetarium, and we're raising funding for that at the moment. We've got some big sponsors who are interested in it as a project. And we're kind of asking people to help us to get us on the way. So in particular, we're building a car park at the moment. So we're interested in contractors or anyone who's got any materials that we could use to build that car park, or any labour that they could help us with. We have to find 10% matched funding for the next stage, so £22,500, of which we've already got £12,000. So we're looking for donations either from companies or from individuals to raise that other £10,000. We have a donations page, which you can see here. When we get to the capital cost of building the project, again, we're looking for some major sponsors or pro bono technical help with the project. And also, just this week, a consultation has been opened by Ashfield Council, and the link to their website is here. That's the Towns Fund. So the Towns Fund is a scheme where each community is being given some money to invest in facilities in the area, and our project developing the Planetarium Visitor Centre has been chosen to potentially be one of those. And they've just opened this consultation, and the more positive comments we get and the more likes we get for our proposal, the more chance we've got of that making their business plan. So if anyone and everyone can go to that website, follow the link through the different parts of the consultation exercise and vote for our project, that would be brilliant. There's even an incentive, because they're giving you entering a draw for a £100 shopping voucher to everyone who fills in the consultation. So please go there and do that. And if anyone wants any more information or wants to talk about the project in any way, then that's me, Steve Wallace, and that's my email address. So feel free to get in touch. So without any further ado, we'll get into the talk, and I'll take you through, let's say, distances and distance scales. So I'm going to start off, as I say, I'm going to try and introduce various historical figures as we go through this. So I'm going to start off with Father Ted and Dougal here, just to illustrate why it's important to measure distance. And this, of course, is a classic: is it small or is it far away? Now, when we're on the Earth, most people know how big a cow is. So if a cow looks small, the chances are it's far away. We've also got visual cues in the environment that we live in, because we're all used to that. So, you know, if there's trees in the distance, we know they get smaller the further they are away. So you've got some sense of scale and some sense of perspective. However, when it comes to astronomy, it's not so easy because it's an unfamiliar world and we've got no sense of scale. And I guess the obvious example of that is a solar eclipse. And this is really an example of how the small or far away thing works. Because, of course, from our perspective, when we view a solar eclipse, we see the moon passing in front of the sun, and they're both about the same size. In fact, they're very close to being the same size. So the moon exactly obscures the sun. Now, without any knowledge of distances, you'd find it hard to actually interpret what was going on there. You know, maybe the sun is actually the same size as the moon, and it's just a few miles further away than the moon. So when the moon moves in front of it, it exactly blocks it out. But of course, we all know that's not the case. In actual fact, the sun is about 400 times larger than the moon, but it also happens to be 400 times further away than the moon. So those two effects cause the sun to look the same size in terms of angular diameter, the size that we see as the moon. But if we didn't have any knowledge of distance, we'd have no way of putting a physical interpretation on what's going on. So distance is very important to interpret astronomical data. Now on Earth, it's very easy to measure distance. You just get a stick if you want to measure a short distance, and you calibrate it in some ways. So if you're in Europe or you're in the UK, you calibrate it in millimeters and centimeters. If you're in America, you'll calibrate it in inches. Then you just put your stick against the thing you want to measure and read off the scale how long that thing is. Since people don't want to carry around incredibly long sticks, someone invented the tape measure, which is just a rolled up stick in effect, and you can get tape measures that go tens of meters long and used for surveying, so you can measure the size of a house or a building using a tape measure. It's pretty easy. If you want to go a bit bigger than that, then you get these surveying wheels. You know what the circumference of the wheel is, and it's got a little clicker on it, so every turn on the wheel it moves a counter on one, and you can push that down the road so you can measure how long a road is by wheeling your machine along it. And of course, when we go anywhere in a car's got an odometer. That's been calibrated effectively. It's like the picture on the left. You know what the rolling radius of the wheel is, and that's used to calibrate the odometer. So you can work out how far you've gone by the difference in the mileage between when you started and when you finished. So that's all pretty straightforward and pretty easy. But what about if you can't physically actually get from point A to point B that you need to measure the distance between? Or putting a tape measure against it or rolling something along it. So that's where geometric methods come in, and geometric methods are being used for things like measuring the height of mountains. This happens to be the Matterhorn just because it's the most mountain-shaped mountain I could find, so it looks good on the image. But this method was famously used to measure the height of Everest and to work out that Everest was the highest mountain in the world. And all you do is you form a right angle triangle like we've got here. You measure the horizontal distance, d in this figure, and you measure the angle that you have to look up at to see the top of the mountain. And through a bit of trigonometry, you can work out what the height of the mountain is without physically having to go up the mountain and measure the height. And indeed, you don't even need to go all the way to the base of the mountain to get d. You can go part way there, measure the angle again, you get a different angle. And as long as you know the distance between the 2 points that you measured the angle at, a bit more complicated maths, but you can work out the height of the mountain. So that's how geometric methods work. And as I say, it was used in 1852 to determine that Everest was the highest mountain in the world. So let's go up another scale, get to stuff that's more of an astronomical interest. And to do that, we need to call on the services of this guy, Eratosthenes, who was a Greek. He was born over 2,000 years ago, as you can see from the title of the slide. And he was a scientist and astronomer born in Cyrene, which is in what we now call Syria. And he noticed that if you placed two sticks vertically in the ground in two different cities in Egypt, which is where he was working, then at the same time of day they'll cast different lengths of shadows. And he did that by, we think, putting some sticks in the ground in Aswan, so towards the southern end of the Nile, and in Alexandria towards the northern end of the Nile in Egypt. And he got different lengths of shadows. And he correctly concluded that the reason why the shadows were different lengths is due to the curvature of the Earth, so the sun was shining on the sticks from a different angle. So I guess take that, flat earthers, that we knew that the Earth wasn't flat over 2,000 years ago. So then what he did was, again, a bit of geometry like we did with the mountain. You could work out what the circumference of the Earth was from the length of the shadows in those two different places. So what he did was he got his sticks in those two different cities, same time of day, he measured the angles, and then used his knowledge of angles and the fact that if those sticks were vertical, the lines through those sticks would intersect at the centre of the Earth, and the fact that that angle measured by his stick and the angle at the centre of the Earth are the same, they're called similar triangles. So what he's got there is a slice of the pie, He knows that there's 360 degrees in a circle, so he knows how many of those slices you need to add up to go around the full circle. And so he worked out the circumference of the Earth. Now, we don't know exactly what answer he got, because he was working in a unit called a stadia, which was a Greek unit at the time. We don't know how many meters there were in a stadia. We have estimates. And based on those estimates, at most, we think he was 17% out on what we now know the circumference of the Earth to be. And he might have been as close as only 0.5% out, which I think is not bad for a bloke with 2 sticks or 2,000 years ago. He managed to pretty accurately measure the circumference of the Earth. And that kind of got me thinking, what can you do with a couple of sticks, particularly useful maybe during lockdown. So this is what I did with a couple of sticks. I nailed the sticks together in a right angle, and I set them up so that the vertical stick cast a shadow on the horizontal stick. And over 4 days, either side of I've got the thing here, over 4 days on either side of the vernal equinox, I measured how long the shadows were and therefore how long the angle was, because I knew how tall the big stick was. And based on that, I managed to calculate the latitude of my house, and I got an answer of 52.7 degrees, plus or minus 0.3 of a degree. I looked on Google Earth to find out what Google Earth said the latitude of my house was, and Google Earth gave 53 degrees. Now that means that I had a bias of probably 33 kilometers, and when I worked out the errors, my errors were plus or minus 33 kilometers. But with a stick on my drive, I managed to work out my latitude to within 33 kilometers. So it just shows what you can do with a couple of sticks. You can see there I also put a thermometer on it. I'm not going to go into too much detail about that bit, but just to demonstrate what you can do with simple equipment, I measured the temperature through the course of a day when it happened to be sunny. I calculated what the insolation should have been from the sun, and you can see from that graph that my temperature curve, the ones with the solid line through the dots, peaks in temperature a little bit after the amount of energy arriving from the sun peaks. And the reason for that is the sun warms the ground up, the ground stores heat, so it takes a little bit longer for the maximum temperature to rise. So the maximum temperature always lags behind the maximum amount of sunlight. So there's lots of things you can do with 2 sticks and a thermometer. So I just thought I'd just drop that in for interest. So the next person in our story, what we need to take the next step in terms of measuring increasing distances is this guy here, Nicolaus Copernicus. Obviously, we know Copernicus. He's very famous for developing the heliocentric model of the universe, of the solar system, where the sun is at the center of the whole solar system and not the Earth, as was previously thought. But he also measured the scale of the solar system using trigonometry, and he's probably less famous for that, even though it was a very important experiment. And in the next slide, I'm going to show you the method that he used with reference to one of the inferior planets, Venus. So again, it's just a geometric method. You can use geometric methods for the other planets as well. So the planets further out than the Earth that he would have known about were Mars, Jupiter and Saturn. But this is the method that he used for Venus and for Mercury. So what you do is you measure what's called the greatest elongation of Venus, or you observe the Sun and Venus and you wait until their angular separation is as big as it can possibly be. And when that's the case, you form a triangle like this between where the Earth is, where Venus is, and where the Sun is. It's sort of right angle triangle. And what you can do, again, like we did with the mountains, you can work out how far Venus is away from the Sun. But hang on, there's a problem here. When we did the mountain, we knew how long the baseline was because we could measure the distance between where we were standing and the base of the mountain. He had no way of measuring how far the Earth was from the Sun, so he could only work out how far away Venus was in terms of how far away the Earth was. So if we call the distance from the Earth to the Sun 1 astronomical unit, he could only say that Venus was a certain amount of that astronomical unit away from the Sun rather than doing it in miles or doing it in kilometers. So, and he did the same thing for all the other planets that were known in his time as well. And these are the results he got. Again, an astronomical unit, which is the distance between the Earth and the Sun. You can see for yourself there, just going to Venus, he got 0.72 astronomical units. And the current modern measured value in astronomical units is also 0.72. And if you look at that list of 6 planets, you realise he was incredibly close, and it's remarkable all those years ago how close he managed to get to the absolute scale of our solar system, just using those few simple tools. Now, this slide uses astronomical units as a scale, and 1 astronomical unit is the distance between the Earth and the Sun. When we're talking to Scout and Cub groups, one of the things that we do is try and get a better sense of that scale by using familiar objects. So I thought I would just go through that briefly. This is a scale that was developed not by us but by someone else. So if you assume the Earth is the size of a peppercorn, that would mean the Sun is about the size of a bowling ball, and on that same sort of scale they'd be roughly 25 meters apart. So you get a bit of a sense of scale for the solar system there. If you do those calculations, again the peppercorn scale for the rest of the solar system, and you look at the column on the right here, the numbers that aren't in the brackets are meters apart, so how far they're apart on the peppercorn scale in terms of meters, and the ones in brackets are the astronomical units, so the numbers that were in Copernicus's scale. And you'll see there on that scale, as I said, the Earth's 25 meters away from the Sun. By the time you get out to Pluto, even on that quite small scale, Pluto would be 1 kilometer away from where we put the bowling ball representing the Sun. So it just gives you a bit of a feel for the size of the distance between the planets in the solar system. And interestingly, on that same scale, Jupiter's about the size of a medium-sized conker. So you get an idea of the scale. So we had to wait over 150 years after Copernicus to properly calibrate his scale of astronomical units. And that was done independently, separately, but they got the same answers by Giovanni Cassini, 1625 to 1712, and John Flamsteed, who was the first astronomer royal here in the UK. And they both basically came up with the same idea, although their exact implementation was a little bit different. Of course, Cassini's best known for being a fantastic visual astronomer. He was the first to spot the gap in the rings of Saturn, which is why the gap's called the Cassini division after him. And he also co-discovered the Great Red Spot on Jupiter and was the first person to observe the differential rotation of the cloud bands on Jupiter as well. So he was obviously a fantastic astronomer. As I've said, John Flamsteed was the first astronomer royal in the UK. So how did they calibrate the scale is the question. So we knew one astronomical unit was a distance. Well, what they did was use the phenomenon called parallax. Now we can all see what parallax is if you hold a finger up at arm's length and look past that finger to some distant object. So if I do it now, I can see the house across the road. And if I close one eye and look at my finger, and then I swap to closing the other eye and look at my finger, it appears to move slightly against that distant background, and that's called parallax. And what Cassini did was use that same principle, except looking from the Earth to Mars and using the background stars as the distant object. Now, the further something away is, the longer you need your baseline, so just closing one eye and closing the other eye isn't any good anymore. You've got to put some miles between those two observation points. He was working in the Parallax Observatory at the time. He got a colleague to travel to Cayman Island off the coast of South America to make that baseline as long as he could. And even with that baseline, it was still a very small angle they were measuring, so it was very difficult to do. And so using that parallax method, using a bit of maths I'll come on to a little bit later, he worked out how far it was from the Earth to Mars, and it turns out he got it accurate to within about 7%. So again, a very good result given the simple tools they were dealing with. And once he knew the distance from Earth to Mars, he could work out the distances from Earth to the Sun, and from Mars to the Sun, and from all of the other planets to the Sun as well. So he calibrated the scale of the solar system using this parallax method. Flamsteed did pretty much the same thing, except instead of going from one place to another on the Earth, he stayed in the same place and allowed the motion of the Earth to change his vantage point to get the two different angles. And when they did that, he got the distance from the Earth to the Sun to be 87 million miles, and we now know it to be 93 million miles. So again, a very good result. So now we have a scale for the solar system. Now, of course, these days we have better ways of doing it. We have direct ranging. So this is a picture of a reflector array that was put on the moon by the Apollo astronauts. And what we do now is we fire lasers at that, and we measure the return time for the laser beam, and we can work out how far away the moon is. And we can do it very precisely. So we know from measurements like this that the moon is actually moving away from us at about a rate of 3.8 centimeters a year. We can do similar things with the other objects in our solar system. So this is Mars. Because we have rovers and equipment on Mars, we send radio signals between the two, so we can exactly measure the distance by working out how long it takes the signals to get between them. The other thing that we can do is send radar signals out, bounce them off the astronomical object in the solar system, and measure how long it takes for them to come back as well. So we've got very precise ways of measuring the scale of the solar system. Now, just before I go on to even bigger scale, I just wanted to say a little bit about units. So if we look at how far away our closest star is, Proxima Centauri, it's 40,208 billion kilometers away, which is a bit of a mouthful to say. So astronomers commonly use different units to measure astronomical distances. So you could measure it in astronomical units, the distance between the Earth and the Sun, and you'd find it was 268,770 astronomical units. Or you could do it in light years, the length of time it takes light to travel between the two objects, and it would be 4.24 years. Or you can measure it in parsecs, which astronomers often use, and I'll come on to what a parsec is in a little bit. So just to recap where we are, we've worked out just by using trigonometry how we can measure distances within our own solar system. But we're going to need a different range of measurement methods if we're going to go beyond the solar system, because trigonometry will only take us so far out into the universe. And this is where the concept of the distance ladder comes in. So what the distance ladder is really getting across is that there are a series of steps, a series of different measures about how we measure distance. And each step on the distance ladder is calibrated because it overlaps with the previous step. So we work out how the previous step works. We have overlap with the next step, so that calibrates the next step, and then that calibrates the next step, and then that calibrates the next step. So what I'm going to do in the rest of the talk is take you through 4 of those steps. There's quite a few different steps that people use, but these are probably the 4 most common that I'm going to take you through over the rest of the presentation. So, step 1, we're already familiar with it. It's parallax that Cassini and Flamsteed used to measure the distance to Mars. That will also work to measure the distance to some of our nearest stars. But you need an even longer baseline because the stars are further away than Mars is. But we've got a ready baseline. If you take the measurements over the course of a year, 6 months apart, your baseline becomes the length of the orbit of the Earth around the Sun. And the diameter of that orbit, the distance from the Earth to the Sun, as we know, is called 1 astronomical unit. And the scale works out that if the star you're looking at over that orbit of the Earth measures an angle of 1 arc second, so there are 60 arc minutes in a degree and 60 arc seconds in an arc minute, so it's quite a small angle, then that distance is defined as a parsec. So that's where the definition of a parsec comes from before. The further away the star is, the smaller that angle is, but it's still measurable. So the first person to measure the parallax of a star was this guy called Friedrich Bessel, and you can see the years that his life were in there. So Bessel was a German astronomer and mathematician. Mathematicians amongst you will recognise his name from something called Bessel functions, which are a way of solving differential equations. But he measured the parallax to a star that I've circled in red there in that diagram on the right, and that's 61 Cygni in the constellation of Cygnus. And he measured the angle to that star 6 months apart as the Earth revolves around the Sun to be 0.314 arc seconds. And that works out at a distance of about 10.3 light years. So it's a fairly close star, but not the closest star. Now, our current best measure of that star is 11.4 light years. So again, he wasn't very far out, maybe 10% out. Now, in modern times, we can do much better than that, and the best method we have is the Gaia Space Telescope. Now, that measures angles to lots of stars. In fact, it's measured the distance to over 1.3 billion stars by parallax methods like Bessel used. And the accuracy of the Gaia satellite is such that it can measure angles as small as 7 micro-arcseconds, which is about 20 billionths of a degree, the angular degree. And that's the equivalent of measuring the thickness of a hair from about 100 kilometers away. So that's how accurate the Gaia Space Telescope can measure angles. Now, I've drawn this kind of crude circle to indicate the distance that it can measure those angles at. But that circle is not very accurate, really, because the distance depends on which direction it's looking, so it can't really see all the way to the centre of the galaxy. It's easier to see in some directions than others. But nevertheless, 1.3 billion stars we now know the exact distance to by the parallax method that was developed by Bessel. So, step 2, that only takes us so far, about the size of that circle I've just shown you. The second method involves the inverse square law. Now, the inverse square law sounds complicated, but all it really says is if you get twice as far away from something, a source of light, then that light gets 4 times fainter. So twice as far away is 4 times fainter, 3 times as far away it's 9 times fainter, 4 times as far away it'd be 16 times fainter, etc., etc. So there's a relationship between how bright something is and how far away it is. That's really obvious. So I'll show how that's used to measure distance. We need to introduce someone else, and this time it's this lady called Henrietta Swan Leavitt. Now, she was born in Massachusetts in 1868 and ended up working at Harvard College Observatory as a computer studying astronomical photographic plates. Those of you who've seen the Hidden Figures film will be familiar with the term computer as it was used before the actual electronic computers came on. And the computers were people who basically did lots of maths and processed data. You know, NASA had them famously in the Hidden Figures film. What Henrietta Leavitt was doing was processing the plates and looking at the brightness of stars. And she started studying variable stars in the Small Magellanic Cloud. She noticed an interesting result, and that result is shown in this figure here. So this figure is taken directly from her paper that she published in 1912, called The Periods of 25 Variable Stars in the Small Magellanic Cloud. And what she found was, well, first of all, I'll just explain this graph. The y-axis, so the up and down axis, is magnitude, and the horizontal axis, the x-axis, is numbers of days. So the number of days goes from 0 up to 2.2 days. Magnitudes, because it's a reverse scale, goes from 16 at the bottom to 12 magnitudes towards the top. And what she found was the brighter the star was, the longer it took to go through a cycle of variation. So these were stars that varied from a large amount of brightness to a small amount of brightness, called variable stars, Cepheid variables, and they went round that cycle every couple of days. And she found this relationship, a straight line between how long it took to go around repeated brightness cycles and how bright the actual star was itself. Now, she knew that they were all pretty much the same distance away because they were all in the Small Magellanic Cloud, so to the first approximation they were all the same distance away. So she realised that must be an intrinsic property of the star and not because some of the stars were different distances away to some of the other stars. And this is a more modern plot of the same thing. So again, we've got magnitudes up the side and time along the top in this case. And the magnitude's been measured over a few days. And you can see there's a periodic variation in brightness in the star, which can be plotted and can be measured. So how do we use that to measure distance? Well, it takes a little bit of explaining, but I'll go through it in this graphic here. So the first thing you do is you measure the brightness of a bunch of Cepheids at known distance. How do you know the distance? Well, you measure the distance to some fairly close Cepheids using the parallax method that we just talked about. That's what I meant by the distance scale, the distance that are overlapping. Because you know the distance and you know the brightness, you can use this equation to work out how far away it is. or sorry, you can convert it to absolute magnitude because you already know how far away it is. So little m is the magnitude you measure. Big M is what we call absolute magnitude, which is how bright the star would be if it was a distance of a distance at 10 parsecs away. Big D is the distance. So you plug the numbers into this equation and you can work out the absolute magnitude of the star. What you then do is plot a graph of that absolute magnitude number against the period, how long it takes to go through its brightness cycle, and you get a graph like this. So along the bottom, you've got the period, how long it takes to go through brightness, and up the y-axis, you've got absolute magnitude, big M. Now what that means is any star that's further away that's a variable Cepheid star, so you can't measure it by parallax, all you've got to do is measure the period of variation and its magnitude, and then what you do is you use the period of variation and you draw a vertical line up on that bottom graph that I've shown you. You take that line across horizontally and you know the absolute magnitude therefore from that graph. And because you know small m and you know big M, you can plug it back into that equation on line number 2 there, and you can work out the distance to it. You have to go through a number of steps, but it means you can use these particular sort of variable stars to work out how far it is to stars that are further away than you can use the parallax method for. So what that does is introduce the next character that you'll be familiar with, another famous name called Edwin Hubble. Hubble studied for his PhD in astronomy at Yerkes Observatory, which was owned by the University of Chicago, and he got his PhD in 1917, and his dissertation was called Photographic Investigation of Faint Nebula. Now in 1919, he got a job at Mount Wilson Observatory where he got to play with a new 100-inch telescope. Now at that time, there was a bit of conflict going on in astronomy, so sort of around the turn of the last century, where astronomers could look up into the sky with the telescopes and they saw nebulosity, and they knew some sort of nebulosity like the one on the left, the Orion Nebula, was within our own galaxy, but they could also see nebulosity like this stuff on the right. And they didn't know what that was, and they basically, there was an argument. Some people said that was stuff inside of our galaxy, some people said it was stuff further away outside of our galaxy. And Hubble used the variable method that Henrietta Leavitt came up with to measure the distance to M31, and he demonstrated that it was actually outside of our galaxy. So he was the first person to prove that there were these island universes, as they were called, further outside of our own galaxy, and that significantly expanded how big everybody thought the universe was. Now he came up with about 1 million light years, and it turned out he was about a factor of 2 out, and that's because he didn't know at the time, no one knew that there were actually 2 different sorts of variable star, and they have different calibrations. He was using the wrong sort for his measurement, but nevertheless he demonstrated it was a very long way away. And of course we now know M31 as the Andromeda Galaxy, and in fact it's a galaxy that's even bigger than our own galaxy, and it's home to about 1 trillion stars, so it's perhaps 5 times larger than our own galaxy. So the useful range for Cepheids, because obviously as they get further and further away they get too faint to measure, is a few tens of millions of light years. And at that scale you can pick up quite a lot of galaxies, and you can see each of those dots on that graphic there as a galaxy. So that's the sort of picture of the universe you can get using Cepheids to measure distances. So you can see out to the Virgo cluster and things like that. Next step, because you run out of brightness on Cepheids, is using type 1 supernova. Now, what they are is a white dwarf with a companion star. So you get a white dwarf when a star the sort of size of our sun or a few times larger than our sun dies and leaves the remnant core behind called a white dwarf. And what happens is the companion star in this binary system gradually loses its atmosphere to the white dwarf, until the mass of the white dwarf, that M with a circle with a dot on it, stands for sun masses. So 1.44 means 1.44 times the mass of our own sun. So that material piles up on the surface of the star until it gets that heavy, and when it gets that heavy, you end up with a runaway thermonuclear reaction and the white dwarf explodes. Now, because they all detonate at the same mass, they all have the same luminosity, and that luminosity is something like 5 billion times how bright the sun is if you were the same distance away from it, that is, of course. So that then becomes what's called the standard candle, because you know how bright every one of those is when they go off. By measuring how bright it appears to be, you can work out how far away it is using the inverse square law.
Okay.
So just give you an example here of how bright these things actually are. So you can see here, this is the Pinwheel galaxy, which is about 21 million light years away. The image on the left where the arrow is, the supernova hasn't gone off. The image on the right, the supernova has gone off. So you can see how bright that single explosion is compared to the brightness of an entire galaxy. So you can measure these things a very long way away. Just another example, this galaxy is, incidentally, the one on that previous picture, it got to a magnitude of about 9.9, so you could have saw that with a reasonably small telescope. This one is in a galaxy 55 million light years away, and it was observed in 1996, and the supernova is that star on the bottom left of the picture. And again, you can see how bright that is compared to the whole galaxy. So you can use these things for a very long
I don't know why, but
range of
sound's
distances.
gone.
I've just heard you. I'll press on. I'm assuming everybody else can still hear me. Yeah. So the useful range for type 1a supernova are about this. So you're up to a few 100 million light years this time, and on that sort of scale, you're starting to see large-scale structure in the universe. So again, each of these dots in this simulation is a galaxy in its own right. They're not stars. We can hear you, Andrew, so I'm not sure why. We are recording this. You can start to see large-scale structure in the universe here. So you can see patterns. You can see galaxies aren't evenly spread over the universe, and you can start to see these filaments of galaxies being formed. So, okay, so that doesn't get us to the whole universe. So what do we do next? So for the final step on the distance ladder I'm going to talk about, we're back to our old friend Edwin Hubble again. Now, the other thing he's famous for, other than just determining the distance to the Andromeda Galaxy, is proving that the universe is expanding. And this is a cut and paste of the graphic that he put in his 1929 paper, where he was measuring the recession speed of galaxies, i.e. how fast they're moving away from us. So the y-axis, the axis up the side, is speed, so 1,000 kilometers there an hour, or sorry, a second, I should say. And along the bottom is parsecs, so how far the galaxy is away. And he got this graph, and that demonstrated that the universe is expanding, because the further something away is, the faster it's moving. So it's a bit like an explosion. Incidentally, how he measured it was by measuring the spectrum of those objects. So when we measure the spectrum of something, we can see these absorption lines, a bit like a barcode, and that corresponds to different elements in what you're looking at. So you can measure the wavelength of one of those lines, or a couple of those lines, and then you find if that object is moving away from you, then those lines are shifted towards the red end of the spectrum. So the wavelength is stretched, it becomes redder. And there's quite a simple equation that you can use, where you measure the wavelength of those lines in the lab, you measure the wavelength in the object that you're looking at that's moving, and by taking the difference in those wavelengths and dividing by the lab wavelength, you find that equals the speed that the object's moving divided by the speed of light. And just by rearranging the equation, you can work out how fast it's moving. Now, the reason why that demonstrates that the universe is expanding, I put this little thing together to show you. So say you've got an elastic band tied to a wall, and you've got point A marked on it at 1 meter, and you've got point B marked on it at 2 meters. And in 1 second, you stretch that elastic band to twice its length. So point A is moved to point B, and point B is moved to where it nearest. So point A is moved 2 meters away, point B is moved 4 meters away, because you've stretched it. If you do a simple bit of maths, you find that point A is moved at 1 meter per second, whereas point B is moved at 2 meters per second. So that just demonstrates that the further something away is, the faster it moves, even though the universe is all sort of stretching at the same rate, like blowing a balloon up. So that's how he demonstrated that the universe was expanding. So how do you use that to measure distance then? Well, you take Hubble's graph, so this graph here, you know how fast something's moving, and you know how far away it is. You've worked out how far away they are using the supernova method that we talked about in the previous step. You measured the velocity by measuring the spectrum, as I've just described. So then for things that are too far away so that you can't measure them using the supernova method, you just extend the line on the graph up, and then you measure its velocity using spectroscopy, and then you just simply read down onto the bottom axis of the graph, and you know how far away it is. So using that method, you can pretty much measure the distance all the way out to the edge of the universe. In fact, that's what it is used for. And when you go to that scale, you start to see something called the cosmic web. So this web, all the light areas there are actually galaxies, and you can see there's this complex network, complex web of galaxies with voids in between, like holes in a sponge almost, where there's not very many galaxies at all, and then other areas where there's quite a high density of galaxies. So people, astronomers, can really use distance measurement to determine what the very large scale structure of the universe is, and then that helps to work out how it was formed and how it's going to evolve. So measuring distance is absolutely essential to astronomy. You wouldn't be able to get anywhere with understanding the physics of what's going on without being able to measure distance. So just in summary then, parallax is the first method. That's an absolute method because all you have to do is measure angles. That's good to about 30,000 light years. Variable stars is the next method. In fact, everything but parallax, you've got to know something about the physics of what you're measuring. So it's subject to change if somebody comes along and says the physics of what you've been measuring is different to what you thought it was. So these scales do get adjusted a bit from time to time. Then you've got supernova that overlap with variable stars. That takes you out to about 10 billion light years. And then you've got Hubble expansion of the universe, and that takes you out to the edge of the universe. As I said at the beginning, there are other methods that are used, but pretty much they're the four common ones and the four most normally talked about. So thank you for listening, and that's the end of the talk. Thank you.